Okay, so let's look at something else. We're going to look at work and the dynamics. And work is something that we know. From grade 12, you've known what work is. You have also defined what work is. All right. Now here, I want to give you a very comprehensive definition of work. All right. Today we are going to define work as the transfer of energy when a force causes a displacement, all right, of an object. We are calling it the transfer of energy, okay, transfer of energy when a force F causes a displacement on an object. Okay, this work is a scalar quantity. It is more of a value than a vector itself. So whatever that you're going to calculate, you're going to get a value. That's what we mean by scalar quantity. Now we know that if W will be denoted as work, work is the product of the force and the displacement. All right. Now, before I add anything, displacement D. This is what you have defined work from the your O-level perspective. But we are going to add something else. Let's say that this is the Cartesian plane, okay? And the displacement is taking place in the x-axis, right? When we say displacement, we mean the change in distance. All right, so it is taking place in the what? In the x-axis. So let's say we have x1 there and x2. You should be able to recall that this distance here just called dx, or delta x, which just means the change in x. So if this work is transferring energy from this point here to that point, remember we're calling it for the transfer of energy. So this force is transferring energy from this point to the other. It means there's a change in displacement. That change in displacement is what we're calling delta x. Are we together? So we're going to say work is equal to, this force is also acting in the x-axis, all right? And we are going to call that as dx. So we are moving away from just displacement, but we're going to call it dx, all right? Now, we are going to make assumptions, all right? We are going to make what? Assumptions. Let's say this is a linear relationship, all right, of work, also of a force and displacement. Now, let us assume that the displacement, so the force is applied at a certain angle. We know here the angle is just what? 0 degrees. It's a straight line, so the angle is just 0 degrees. What if a force is applied at an angle other than 0 degrees? How do we treat that? All right, so take note that for work to be done, the force and the displacement should be parallel to each other. So what do we mean? We mean the force should be what? Parallel to the what? To the displacement. Let me call it dt. Yes, delta d to mean the change in displacement. They should be parallel to one another. So let's assume this is a box. Okay, and this is the where the displacement is taking place. So let's say this box comes here. It makes a displacement and finds itself there. All right. And of course, let's say the box up to there, and of course. So we call this, let's call this as delta x, okay, in that direction. So this is the box, all right? So let's say the force is applied at some angle, okay? This angle here. You see the angle? This one's the angle. So if I do this, the angle I'm talking about is this one there. You will discover that this angle here has got this force. Now it will be resoluted into two. There will be the force y there. There's also be the what? The force x. But remember that for work to be done, the force and the displacement must be parallel to one another. So we are saying this force in the x is the only one which is parallel to the what? To the displacement. So we are saying work is therefore given by force in the x, all right, displacement, but cause what? Cause in the x, I think if you've done vector analysis, you know that the x-axis is associated with cosine, all right? So we are going to add the issue of the angle there. So cos theta. So to rewrite this one properly, we are saying this is f, okay, cos theta. Let me do this. Fx dx. Now what is fx? Well, fx is just the component of the actual force in the x-axis, which is what? Which will be f cos theta multiplied by what? Delta x. This will be the formula to use anytime a force is applied at a certain angle. Now, it's not always that it will be in the x-axis. Sometimes the displacement can also be in the y-axis. As long as the force that you're looking for and that displacement, they are parallel to each other, then work is what? Is done. That is what you need to know. All right? So here's an example. So we have a toy car. Let me just completely label it. And the force is applied at an angle of 25 degrees. The question is calculate the work done in moving the toy horizontally through a distance of 265 centimeters. All right, so we've just seen that. We just calculated that the formula is here. And because, you know, the distance will always be in the x-axis for this type of arrangement. So the distance is in the x-axis. So we're talking about dx here. So we're just applying the same formula there. Okay, we know that, okay, work done is force cos theta, then what? Changing x. Now here is the stuff. All right, so the force is 1.5 newtons. All right, we know that. Then cosine 25 degrees. Okay, then multiply by. Now take note that the distance is actually in centimeters, so we need to convert that one into meters. So we can just say 265 centimeters. We divide by what? 100 centimeters, then multiply by meters. Remember, this is dimensional analysis. We do the correct thing. All right. So by doing that, let me just punch everything on the calculator. All right. Okay. So I end up having an approximate of 3.6 joules of work. This is the work being done in the x-axis. Because in the y-axis, there's no work. In the y-axis, sorry, there's no work. Work is only in the x-axis because this force here and the distance, they are parallel. Okay. So we needed, so the distance that we needed, the force Fy, Fx. Fx times x is what we've got in here. That's all.